Hello everyone. This is lecture 280. We are taking a new topic, that is plastic design. So before understanding this design, इसको समझने के लिए of steel. Actually this plastic design is for steel. So हम यहाँ पर we are drawing the stress strain diagram of mild steel. माइल्ड स्टील का स्ट्रेस और स्ट्रेन डायग्राम हम यहाँ ड्रा करते हैं. तो यहाँ पर आप देखोगे कि ये डायग्राम यहाँ स्ट्रेस दिखाया है और ये स्ट्रेन दिखाया है. तो किस तरह से ये हमारा स्टील बिहेव करता है. तो इफ O to A आप चलेंगे तो स्ट्रेस is proportional to strain, you can say. Yeah, this you can say this is something like that this is a straight line O to A. O to A is a straight line, if load is raised up to A and the load is removed, the body recovers, comes to its original position. जब इसमें स्ट्रेस लगाते हैं फोर्स डिवाइडेड बाय एरिया, तो क्या करेगा, इंक्रीज करेगा. तो ये वी आर गेटिंग देयर इज सम स्ट्रेन, यू आर गेटिंग स्ट्रेन. दिस इज स्ट्रेन फ्रॉम O to A कैन बी रिकवरेबल. तो ये जो पॉइंट है दैट ओबेज द हुक्स लॉ, दैट O to A obeys the Hooke's law. So this is called limit of proportionality. If you remove the load, if you remove the stress, it will come to its original position. If a steel rod is there, if you try to pull it, then it will get some stress, and strain will be developed. That will be increased. But if you remove the stress, the strain comes to its original position and the shape remains same. So though point O to A, that point is called the point of proportionality. That is, OA is a limit, follows the limit of proportionality. This is proportional limit. A can be said as a proportional limit. So there is a proportion. Proportion means the stress which is removed will be recoverable and strain will disappear. But from A to B, this is not happening. A to B, it is not happening. It is, although non-linear means if you remove the load or stress, this will be not recoverable. This will be already deformed. But the deformation is elastic. A to B is deformation is elastic. It is just a point from A to B is very near, where the if you remove the stress, this will not recoverable. So that is point is called, this point B. B is non-linear, and this A to B is elastic. This is elastic. Now the steel is stresses, but if you remove the stress, it will not recoverable. That point A to B is a non-linear, means does not follow that equation of Hooke's law, or that is the if you remove the loads, nothing will happen, will deform already. So that is your elastic behavior. Now what will happen next? You will reach a point 1, which is the upper point. You get a stress at this point. This is upper yield point. Now yielding is starting, then it droops, it goes down, and we get a point D, which is lower in respect to C. If you read in the dial, the higher reading is coming, then a lower reading will come. So corresponding to lower limit, that signals from the dial, that you note it down. That is your lower in point. So in this process you will find that one is upper limit point and one is another point which is less value in terms of your stress, but the strain is different. If strain is different, here strain is different, here strain is different. Here the strain is somewhere more in respect to upper yield point. The strain variation will be slightly higher. तो क्या हो रहा है, यहां से O से A तक तो हुक्स का लॉ फॉलो कर रहा है. इसका मतलब ये आप स्ट्रेसेस में स्ट्रेस को इस लिमिट तक करेंगे जिससे हटाने के बाद वो रिकवरेबल होगी. लेकिन एक पॉइंट ऐसा आएगा ए से ऊपर बी पॉइंट जहां पर कि नॉन लीनियर होगा, ये बिहेव नहीं करेगा. और उसके बाद स्लाइटली एक पॉइंट ऊंचा जाएगा जहां पर कि आपको एक स्ट्रेस हायर स्ट्रेस मिलेगा. उसके बाद फिर आप देखेंगे कि मटेरियल का डिफॉर्मेशन शुरू हो गया है और नीचे एक लोअर पॉइंट आएगा और उसके बाद स्ट्रेचिंग शुरू हो जाती है. मीन्स आपकी जो स्ट्रेन हार्डनिंग ये इस जोन से यहाँ से जो है आपका स्ट्रेन की हार्डनिंग आप स्ट्रेन होना शुरू हो जाती है. हार्डनिंग आपकी स्ट्रेन की हार्डनिंग हो गई या प्लास्टिक डिफॉर्मेशन यहाँ शुरू हो जाएगा. प्लास्टिक डिफॉर्मेशन. नाउ फ्रॉम द लोअर पॉइंट your plastic deformation will start. Means the steel or any plate will get stretched. The cross section will get somewhat reduced and higher strength you will get. So at this point, this is your lower yield point and this is the point where the ultimate strength is reached. Ultimate tensile strength is reached. So from this point, the narrowing of the section, if you take some steel bar or something like that, if you take like this, so there is a pull, tension. So what is happening at this point, there is a narrowing of the section. This section will be narrowed something like this. So this section is narrowing of section. This section is reduced. They are going to rupture and they are likely to be break after it. So this point is E point where we are getting this narrow section, necking of this section. This is called the necking of section. Necking. This is means the cross section is being reduced and stress is very much. So stress because the F force divided by area is reduced with respect to original area, reduced. So this will be higher value. So this is the E point which is ultimate tensile strength. No more strength can be gained by this steel में और इससे ज़्यादा strength बढ़ाया नहीं जा सकता है. So that is called the ultimate tensile strength. And F is the point strength at fracture when the material cross section fails. So this is the stress which is that is load, whatever load is applied divided by original area. So we will get the stress at fracture. So the behavior of steel is behaving from CD D to E is in a plastic and hardening zone. Then what will happen if we are designing the material with respect to this lower yield point. We are taking the stress at lower yield point. This is your lower yield point. With lower yield point, for the workable stress, we are dividing some factor of safety. Lower yield point is your YFY, means yield stress. Yield stress is taken at lower yield point. Whatever be the lower yield point, that will correspond to your yield stress. And if you divide some factor of safety, you will find C working stress या that is working stress या allowable stress. So allowable stress is nothing that is lower yield stress divided by some factor of safety. So यहाँ पर क्या कर रहे हैं कि हम जो भी स्ट्रक्चर डिजाइन कर रहे थे अभी तक वो इस स्ट्रेस के रिस्पेक्ट में कर रहे थे, इसमें फैक्टर ऑफ सेफ्टी वर्किंग के लिए ले गए, लेकिन जो यील्ड स्ट्रेस हम मैक्सिमम लेते थे ये डिजाइन करने के लिए इस Fy तक ही लेते थे। लेकिन इसके आगे जो है ये आपका बिहेवियर जो है स्टील का वो प्लास्टिक रेंज में चला जाएगा, डिफॉर्मेशन होगा लेकिन ब्रेक नहीं होगा। तो इसकी वजह से जो और भी सेक्शन में जो अनस्ट्रेस है, जो इस स्ट्रेस को नहीं गेन किए हैं, उस स्ट्रेस को गेन करा करके इसकी स्ट्रेंथ को हम लोग बढ़ा सकते हैं। वी कैन इंक्रीज द स्ट्रेंथ कैरिंग कैपेसिटी ऑफ दैट वेरी सेक्शन by utilizing this hardening and plastic behavior of steel. So यहाँ पर इस स्ट्रेस डायग्राम के माध्यम से हम ये बताने की कोशिश कर रहे हैं कि नाउ द मटेरियल और ये इस जोन का जो हम डी से यहाँ ई के बीच का जो जोन का यूटिलाइजेशन कर रहे हैं, उस यूटिलाइजेशन में हम लोड को देख रहे हैं कि मैक्सिमम किस ब्रेकिंग स्ट्रेस तक, यहाँ तक इस स्ट्रेस तक कितना लोड को ये वहन कर सकती है, कितनी कैपेसिटी है। सो दैट कैपेसिटी विच इट कैन टेक अप, दैट डिजाइन इज कोलैप्स मेथड ऑफ डिजाइन और द plastic design. We look over the collapse load which the steel can take, and the behavior of that steel is just like a plastic. So that is the plastic design. The method in which the plastic deformation and hardening of strain is being considered. The method in which hardening of steel hardening strain and plastic deformation is considered in the steel, that is called the plastic design. This concept is based on the deformation which is taking because of the plastic behavior of the steel, and hardening, strain hardening. If you include this, then this design will be called as a plastic design. So how this plastic design can be done? So for that we can have some graph. So this stress strain diagram is modified in the sense that this diagram is like this. This is Fy is corresponding, and this is a straight line. So this is a bilinear diagram. This is one line and this is another line. So this is depicting the elastic behavior. This is elastic strain, and this is a plastic behavior. So this is a plastic behavior, and this is elastic. So this is elastic and plastic, both behavior are linked in this modified stress diagram. So this is ideal elastoplastic stress strain diagram. This is ideal elastoplastic stress diagram. So हम ये जानने की कोशिश करते हैं कि स्टील का जो बिहेवियर है वो केवल यहाँ तक ए पॉइंट या बी, सी या डी पॉइंट तक ही कंसंट्रेट नहीं हो सकता है, बल्कि इसके फर्दर भी इसको हम लोग स्ट्रेस दे सकते हैं, फर्दर इसको एलोंगेट या इसका डिफॉर्मेशन हो सकता है। तो डिफॉर्मेशन होने की बजाय जब ये स्ट्रेस को हम यहाँ रखते हुए स्ट्रेन में परिवर्तन करते जाएंगे तो उसमें क्या है कि दिस विल बी एबल टू टेक मोर लोड्स। इसका मतलब ये हुआ कि इफ यू इंक्रीज द लोड व्हाट विल हैपन विल लुक आफ्टर, कैसे विल सी द स्ट्रेस डायग्राम ऑफ एक इलास्टिक बॉडी, and then we'll see how this changes. So there are some assumption in plastic theory में some assumption है कि steel having property of ductility क्योंकि ductile है, leads to deform in plastic stress without fracture. बिना फ्रैक्चर के प्लास्टिक स्ट्रेस में इसका भी डिफॉर्मेशन हो सकता है। तो इस प्रॉपर्टी को यूज कर रहे हैं। स्ट्रेन डिस्ट्रीब्यूशन इज लीनियर, प्लेन सेक्शन बिफोर बेंडिंग रिमेन प्लेन आफ्टर बेंडिंग। जो आपका सेक्शन प्लेन है वो प्लेन बिफोर और आफ्टर बेंडिंग में आप जो है वो बिहेव करेगा आपका, दिस विल बिहेव समथिंग लाइक दैट। तो यहाँ पर हम लोग इसको अभी समझने की कोशिश करेंगे कि व्हाट इज द स्ट्रेस स्ट्रेन डायग्राम modified to elastoplastic stress strain diagram. Now this diagram is modified to elastoplastic stress strain diagram. The stress, tensile stress and strain, same is the relation between the tensile stress and strain is same as the compressive stress and strain. स्टील के टेंसाइल स्ट्रेस स्ट्रेन का रिलेशन कंप्रेशन के स्ट्रेस और स्ट्रेन के रिलेशन सेम है, द रिलेशन सेम है। दैट ऑल कनेक्शंस प्रोवाइडेड सैटिस्फैक्टरी कंटिन्यूटी इज टू ट्रांसमिट plastic movement. So plastic movement can be transferred through the joints, and the loads which are coming on this beam or something like that will share the proportionate ultimate load according to design. So this will be something like that we can understand. Now how this beam can be designed, let's try to understand. इसको समझने की कोशिश करें हम लोग, कैसे करेंगे देखते हैं किस तरह से किया जाए। तो अगर मान लो आप कोई सेक्शन लो, suppose if you take any section something like this, rectangle section is there. So elastic deformation, elastic will be something like that. This is your Fy maybe, and this is your Fy stress. This is, and the moment carried is equal to Fy into Z. Z is section modulus. Z equals to your section modulus, that is I neutral axis divided by y. I neutral axis divided by y. This is your y. This is yt. This is your yc. Maybe like this. Maybe like this. So these are the yt is the y is the distance of extreme fiber from neutral axis. So neutral axis, this is your what. So this Fy, if you go for something like that, this will, you can say this is your elastic deformation. So for the working load, this will behave something like this. If there is factor of safety Fy upon factor of safety is used, so this will be your Fa, F0 या Fa can be stress here, Fa stress can be, so this is less than Fy. This is less than Fy. This is less than Fy. So what we can do, we can do by, if you take some example of loading, if you take some loading pattern, something like that, there is UDL, so load is WA load, then we have this stress diagram. This is stress diagram in which we can always find out the moment Fy into Z. But if you find out the Ma equals to your Fa into Z. If you increase the load from WA to, you can say WA to some more stress, more load is applied, what will happen? This this stress diagram will be change, something like change. So this we can reach up to this point. This point. This is your Fy. We can give the stress up to Fy. So this is the maximum load, the maximum moment which we can carry. This you can say My. You can say My is equal to Fy into Z. This load can be carried up to your stress Fy. So Fy is greater than Fa. So at this point you can ultimately in elastic deformation, in elastic pattern, what you can say that you can go up to Fy stress. If beyond this Wy we increase the load, what will happen? If we increase the load, what will happen? If you see these, if you draw the diagram, you will find this is Fy, but the bottom layers are not being stressed. This top fiber is stressed. So what will happen? Because of the plastic deformation, if you increase the strain from the diagram, if you see the diagram, what is diagram? Like this. This is diagram. If you do not increase but you increase the strain. If you increase the strain, what will happen? This will behave something like this. This will go down like this. So this will be behaved in this way. So some portion may be stressed, something like that. And here will find this is your behavior in this way. So this is behaving like this. This is behaving like this. So some portion is some lower fibers are being stressed to Fy. Lower part are being stressed to Fy, this part. So this is your elastoplastic behavior. This is elastoplastic behavior of steel. Now this is having. What is happening? This is getting change. क्यों चेंज हो रहा है? क्योंकि if you increase the strain, what will happen? The strain diagram will be something like this. The strain diagram will be something like this. Because of the Fy, this is stress. If you increase the strain somewhere, you increase the strain in this way, what will happen? This change will come here. The change will become here. So this will be some strain is there in this diagram. What is happening? This is the stress is same Fy, but strain is changing from one point to another. So you keep on changing the strain, the lower fiber will get stress. Lower fiber will get stress A equal to Fy. Now what will happen if you do one thing, you keep on loading, keep on changing the stress, then what will happen? This will be all the fiber will get stress in this behavior, in this way. So gradually what will happen? Without changing the stress, yield stress, by changing the strain to ultimate strain, we are getting this type of structure, this type of diagram. So this will be total plastic. This is plastic behavior, and this is your diagram in this way. This is your diagram, something like this. So this is your plastic, this is elastoplastic, and this is your plastic. So a hinge will be produced over here. Now what will happen? This will be create a moment. Maybe this is tensile moment, and this will create a moment compressive in this way. So there is a compressive moment, compression, and this may be tension. So what will happen? This, because of this distance may be y1 and this distance may be y2. This T into y1 plus C into y2 will produce moment at this point, at neutral axis. This stage is your plastic neutral axis, neutral axis. This is plastic axis. You can say not neutral axis, but it is plastic axis. The moment at this point is T into y1 plus C into y2. And what is T? T is this is your Fy, and this is dividing this area A 2 by 2 into Fy, and this C is also A by 2 into Fy. So T and C, both this portion is being divided in half. This area is divided, total area of the section is divided in half. That stage in which the both area is divided in half, that line is your plastic line, or this is called equal area axis. This is equal area axis because this axis divides the section in two half on both sides. So this is your plastic axis or the equal area axis. This is called the plastic or equal area axis. So let us try to understand this thing. We can understand this in this diagram. This is your elastic curve, elastic diastasis diagram. This is behaving from workable stress to your yield stress, up to yield stress, which you can design in elastic में आप कर सकते हो. You can take the moment like this, but for the deformation in plastic you have to increase the strain without increasing the stress. So if you increase the deformation taking in constant stress, then the lower fiber will get stress. Up to Fy. Then if you take the Fy, lower one will take the Fy, and slightly all the layer from this part will take up, and this will create a plastic axis, plastic hinge will be created. The moment, both moments T into y1 and C into y2 is giving you moment. Tc1 means Ta by2 into Fy into y1 plus y2, y1 and y2. So this is area half, the section which we have taken, the shape which we have taken, उसका हाफ से जो गुजरेगा, वो उसकी प्लास्टिक एक्सिस कहलाएगी. उसके एरिया के हाफ से जो गुजरेगा प्लास्टिक एक्सिस कहलाएगा. और उस एरिया के सेंट्रॉइड से, इसके सेंट्रॉइड से जो डिस्टेंस लेंगे y1 और इसके y2 लेंगे, वो उसका टोटल मोमेंट है. T और C दोनों के कंबाइंड मोमेंट को लेके यहाँ आएंगे. तो यहाँ देखेंगे this is behaving something like that in this way, and this is behaving in this way. This is your, if it is tension is like this. So compression will be, this is your this way, this will be also this way. Both will be in same way. Compression and tension will give additive. This will give you additive, means this if you going through, this is tensile, so this is giving moment like this, and this is also giving moment. Compression will give a moment like this. So both are giving the moment, So total moment is your A by 2 into Fy multiplied by y1 plus y1 plus y2. So we'll try to understand this by figure, by behavior of this thing, what is happening. Actually, we try to increase the moment. If you try to increase the moment, the stress strain diagram will be changed from this to this, and finally if you increase the moment or you load, then this will behave something like this. This is a plastic behavior, this is elastoplastic, and this is elastic behavior. So we are designing the structure with the help of this elastic behavior, and now if it is designed by the plastic behavior, then you will take this, or we can this plastic behavior, total plastic behavior, we can take in this way. So this is how to understand, and try to make you understand this way. Thank you for being with me.